Okay, we all ready? All right. Welcome to lecture 2 of the math class. So last time we started off with counting. The basic idea of what, let's say, 3 is I think this is 3, I think this is 3, I know that it's 3, that they're the same thing because I can map them like that. That's kind of the fundamental starting point of number. X. We'll get to that. Beautiful X. Last time I mentioned the 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then after that, you get 10, 11, all that, 100, 1,000. You have groups of 10, 20, all that stuff. And then 10 groups of 10, and then 10 groups of 100. 10 is very fundamental in this system. Why 10? So, probably. There are actually other systems employed throughout the world. Our clocks with the 60 and the 12, that kind of comes from Babylon. And they used a base 60 system, at least for some stuff. 60 has very nice mathematical properties. That's why they probably used it. But it really kind of, is terrible for humans because, dealing with 60 things without grouping them is very hard for us. I also read about that one tribe used base 8 because they counted the space between the fingers. Pretty cool. I've never heard of base 5, but I would have thought that would have been a possibility.
School meeting members, this is my wrestling voice for Wrestling Corporation. Wrestling Corporation is going to be meeting at 1:15 in the gym. 1:15 in the gym, be there, be square. If you would like to go, and it conflicts with James's awesome math class of all the mathness, and you don't know which one to go to, come see me, and we will make arrangements so that you can go to both. Other than that, 1:15 in the gym, Wrestling Corporation.
Thank you, Ashley. One other base that is actually quite used a lot, well, actually, a few related bases, is base 2. That's just using 0 and 1. And that's used because in computers, on-off is a very easy state to kind of count, and so that's very natural. And then you have like base 8 and 16 because just having 2 digits is a little, it gets, hard to deal with. Alrighty, so that's a bit about the counting. Now, is 6 larger than 3?
Yeah.
Why? How do we know that?
Because it's 2 3s.
It's 3 more digits.
Okay. So what does more mean? How do we?
Higher than something other.
Okay. How can you kind of? If I say I don't believe you, that's like I say, okay, I've got 6. Okay, that's one thing. I've got 3. That's the thing. How do you convince me that this is more than this?
Took 3 away from it, you would still have things?
Right. So just as sort of the notion of counting is matching, greater than can be a matching as well. So you have kind of like 6 dots here. 3 dots here. And then using the full color at my disposal. Maybe not. This is why people don't put caps back on markers. Now I understand. So you match them up, and then there's stuff left over. So that's the meaning of 6 being greater than 3. So we use this symbol, greater than. So, and so anytime you can kind of match these numbers like that, that works. And it sort of starts kind of fundamentally with the notion of, like, here it'd be really 3 greater than 0 is kind of almost the basic sort of starting point. Right, like I've got 3 here and nothing here. And that's kind of what, I got stuff here and nothing there, so that's the fundamental kind of notion basing on 0. So that's that notion. Now, last time I also went over a bit of single-digit arithmetic. I'll review that a little bit some more, and then we'll get into addition and subtraction with larger numbers. So, 2 plus 5. What is that?
7.
7. So we write equals 7. And going back to basics is, we got 2 dots for 2, 5 dots for 5, and then addition is putting them together. And there's 7 dots, right? So that's the fundamental kind of starting point. Now, one thing to get good at doing a lot of math stuff is, if you look at this, in your head, do not say 2 plus 5. Think 7. If you can try to do that, then things speed up tremendously. The analogy is, like, if you look at this word, do you say T-H-I-S in your head? No, you say this. Imagine if you spelled out all the words, right? Your language ability would just plummet. This is kind of a basic kind of word, you might say. Single-digit arithmetic in general. You look at it, you should just see the answer immediately. It takes a little practice to do that well, but it's just practice. Whenever confused about things, it's always back to counting. Nothing mysterious, it's just getting comfortable with seeing what goes on. Now, 8 plus 5. 13. So, you have a couple options here. One is, do the same thing here, right? 8 dots, 5 dots, count them all up, 13 dots. And then, you know, kind of internally memorizing it so that you're quick with it. But there's another option, a somewhat nicer option. What is 8 near? Something very fundamental. 10. So we can write this as 8 plus 2 plus 3. Now, you don't actually write that like that, but slow steps. And so this is 10, and this is 3. And so whenever doing these kinds of things that go over 10, like 9 plus 6, you say 10, 5, and that's 15. And so it's being rooted in this 10 is a key skill for doing this kind of stuff quickly and efficiently and having flexibility. Alrighty. Let's try a little bit more digits. Let's see. Just so you can test me, Declan. Can you roll these dice and give me two-digit numbers from them?
All right. Well, a 9, 5, 10. The only thing we got as a 2-digit number.
Oh, no. I'll add them together. So like
okay.
10 and 3 is 13, and 6 and 9 is...
9, 28.
What's 28?
Oh.
Just the digits, 69
no,
and
sorry.
13.
I misheard.
No problem. So now we want to add this. So there's kind of a standard method, which is bad. And then there's a better method, which is, well, better. And first there's a better method, which is also bad. So when I look at this, what do I do? I say 69. What is that close to in terms of tens?
70.
70. And 13, what is that close to in terms of tens?
10.
10. So I instantly already know it's 80. So, for example, if I was buying something that was $69 and something else $13, and I want to know if I have enough money in my wallet, and I know I have $100 in my wallet, I'm probably good. You know, that's very often that's all you need to do. All right. But also very often you need details. So, before getting to the actual technique, the setup is, so what is 69? How can I write that in a different way? So, what is this? This 6 says what? I've got 6 tens, right? So that's 60. And then I have 9 ones. And 13 is 1 10 and a 3. So, if I want to add them up,
Wrestling Corporation meeting right now in the gym. Be there, be square.
you just add them individually. The 6 and the 1 come together to be 70. And the 9 and the 3 come together to be 12. And so I've just kind of broken these things. It's like if I had 69 sticks and I had 6 bundles of 10 sticks, and then I had 13 sticks, and one of them was a bundle of 10, and I just put the bundles together and I count the bundles, and that's 70. The only thing I cared about was this leading digit. And then over here, I add that, and, you know, theoretically, you should do it like this. I've been ingrained in another way all my life, so I don't always do that, but, you know, think of the 9 and the 3. 9 is almost 10, but the 2, you get your 12. All right, and then I add these together. So I've got a bundle of 10 and a 2. So 70 plus 10 plus 2, and then 80 plus 2, and then 82 is my answer. So that's the long way of what all this addition means. Obviously, you don't want to do that, right? But that's what it means. It's always good to first start with what does something mean. Okay. Now, let me do it the bad way. All right. So this is what, you know, I was educated in. Most people who have been through math classes have been. Probably if you look at textbooks, you'll see this. It's a bad way. Do 9 and 3. You say that's 12. So you write down a 2. You do a 1. Up here, you say 1, 6, 1. That's 8. And that's your answer. Now it's pretty quick, right? Pretty straightforward, mechanical. But what's the problem? What's the thing that it does wrong?
Small stuff first.
Right. So you're most likely to make a mistake later in your computations, not earlier. And if I were to be off by 1, which digit would I want to be off by 1 on if it was, say, money?
Smaller one.
The smaller one, the 2.
It depends.
I only got one thing.
If you're trying to be honest. You know, the 8 here is much more significant than the 2. And so we want to actually, just as we read from left to right, we want to do the math from left to right. So this was, you know, going this direction, kind of bad as small details come first. Now, why do we do it, or why do some people do it that way? Why do most people do it that way? What? Well, yes, but why? But why was that chosen as the method to be done? Well, this carrying part, right? Once I'm done with the 9 and the 3 becoming 12, I write the 2, I put the 1, and I don't go backwards, right? Like, I'm done with that, and now I can add that up, and I get 82. If you look here, in this kind of more spread out one, I did the tens, and then I did the single digits, and then I have to go back to the tens, right? Like, it seems a little less repetitive in this fashion, but it's still kind of like reorganizing some stuff. So that's sort of why they do it that way. But the advantage of doing it left to right is so huge, in my opinion, that it should be done that way, and it's not too bad. So
I don't see how it's so bad if you get the same answer anyway.
oh, like this? I mean, if you get the same answer, it's fine, but it's more about when you don't get the same answer. Humans are not very good at a lot of arithmetic. This isn't too bad, but add a few more digits, add a few more numbers, and all of a sudden, you know, problems occur.
I mean, yeah, I've done long addition, long multiplication, and that one gets very complicated sometimes.
Right.
Usually don't end up with all the numbers combined.
Right. So a lot of things can go wrong, and it usually happens later in the problem, so you want to get the earlier stuff right where you can. So how can we do, what's a technique for doing it from left to right? Well, you start with the 7, just as before, and then you have the 2, the 9, and the 3. Again, it's like 10 plus 2. The 2 is what matters. You write down the 2, and now you have a 10, and you can just kind of put an underline underneath this to tell yourself that you need to increment it by 1, and so it's 82. So it's kind of a record keeping. You know, notice that, you know, when I do this 6 plus 1, and I have 7, you know, that's already getting close to the final answer in terms of the size, right? Getting the 2 first is not. You're still far. If you just said 69 plus 13 is 2, people would, like, that's laughably wrong. If you say 69 plus 13, 70, you'll still get a little chuckle, but at least it's in the right ballpark. And so you just kind of have that little slash. All right. Let's try another one like this. Daceman, can you roll?
Oh, yeah. A 9, 7,
Looks like,
3, and a 5.
all right, 57 and 39. All right, left to right. 8, and then you got the 7 and the 9. The 9 is just one off from 10. So 10 and the 7 becomes a 6, so that's 6 with 1 left over. So it's 86 plus 10, 96. All right, so left first and then right. If you have something that doesn't actually increment at all, like 57 and 32, you know, you don't have to do any kind of, so half the time, probably you don't have to deal with this kind of stuff. Alrighty. Now, let's try 3-digit numbers. All right. Okay. The long drawn out way, just to kind of remind what all this stuff means. 5 bundles of 100, 7 bundles of 10, 2 bundles of single digits, 3 bundles of 100, 8 bundles of 10, 5 singles, and then you add them up, 800, 15, 0, 150 therefore, and 7. So 800 is kind of close, and now we have the 150, so that's 950, and then the 7 comes along. So that's kind of doing it out with what all the zeros mean. It's important to really get firm in your mind what these placements mean. The 500, the 300, what all that means. In terms of rounding, 572 is close to what? 600. 385 is close to, and so this is approximately 1,000, and that's pretty good. Close to 957. All right. And now let's do it the way that I would actually recommend doing it. It's, again, mostly the same, but 5 and 3 is 8. 7 and 8, 8 becomes a 10. You get a 5 left over. Underline that because you get a 1, so that's 15, and then 7, and so 957. Okay? All right. Now, any questions about that? Okay. All right. I think somewhere. Now let's add some extra numbers. I have a long list of numbers somewhere. No, I don't have a long list of numbers. All right. People call out numbers. Give me some numbers.
7.
Okay. 2 or 3 digit numbers.
14.
14.
14.
652.
652. There's a 1 over here.
29.
29. One more.
47.
47.
47. All righty. So, so the first step is what? We do it intentionally wrong, and we round.
Yeah.
So, looks like there's a lot of 10s, so maybe I want to keep this 652 as 650. I don't know. 14, let's say 10. These two are kind of 10, 10, 30, and 50. That's already, this is like 60, 50, 700, 760. All right? So really quick and sloppy. I've already got, like, when I look at this, I'm not really sure. Probably 700 something, but a little bit of rounding, and then I can do a little better. Now let's do it out, see how we did. So there's only one 100, so I'll just bring that down, 6. 1 and 5 is 6, and then the 2 is 8. Then I got 8 and 4. 2 more for 8 gets you to 10, so that's a 2, and you had a 1. So it's 12, but underline that. 8 and 7, again, that's going to be a 5 and a 1. So now that I've got multiple digits, I'm just going to put out, kind of count it on my thumb, or my finger. So I've got 1, 1, 1 coming from that, but I just keep in my mind the 5. So 8 and 7 is 15. 5 stays in my mind. The 1 stays on my finger. And then the 4 becomes a 9. 2, that's going to give me a total of 11, so that becomes a 1 in my mind and a 2 in my fingers. And then the 9 with the 1 becomes a 0, and I get another 1 on my finger. And then 7. So I have a 7 there. Now I've got 3 things. I could underline this 3 times, but probably at that point, you just want to put a 3 underneath that thing, and then you add 600 and, no, oops, 7. Yep. This is why you round first. I was like, that can't be that bad. I forgot that underline. So if you do anticipate doing this, it might be more sensible to drop the underlines entirely and just write the 1 in that lower level. But anyway, left to right, it can be done. All right, any questions about addition? Okay. Yeah. What comes after addition?
Multiplication or division?
We'll go with subtraction.
All right.
But multiplication is kind of the easier one to go after. Addition, but we'll do subtraction.
All right.
All right, so subtraction. What does subtraction mean?
Getting rid of or taking away.
So 8 minus 2. That's 6. And here, you could do the counting like so. Maybe 2 dots over here. And then you can connect them up, cross it out, and then you count what's left, and that's 6. So that's fundamentally what subtraction means. It's removing stuff from the pile. It can also mean something else, or be used for something else. 2 plus what equals 8? 6. So it's kind of like the same problem. And in fact, you can say, well, I've already got 2. What do I need more? So I cross out these 2, cross these 2. I need 6. So it's 2 different ways, well, 2 different questions that rely on the same kind of underlying mechanism of kind of crossing out. But you know, if you think of the kind of the context of it all, you know, this is like in terms of money, you have $8, and you're paying out $2, and you have $6 left, right? Here, it's like, oh, I want to buy something that's $8. I've got 2. How many more dollars do I need, right? Kind of 2 very different perspectives. And that's somewhat relevant to something like this. 3 minus 4 is what? So, could mean minus 1, or it could mean 0, right? So if I owe somebody $4 and I've got 3 and I give them $3, right? Maybe I go into debt by $1, in which case I'm minus 1, or maybe I'm out. Like in Monopoly, you run out of money, you're not in debt, you're just out of the game. So, you know, there is this question here as to what one would mean. Depends on context, but in general math, we introduce sort of negative numbers. So, wow. Okay. And sort of, you know, there's a number of different ways of kind of defining it. At first, it just kind of comes out as, you know, again, you can kind of think of it as you've got 3 and 4. You've canceled out these. You've canceled these out. You've got 1 left over. But now it's kind of negative, and you just call it negative, right? So that's just kind of means a negative number. And, you know, it's almost like we kind of color the numbers. I think it took quite a while for negative numbers to be kind of used, largely because it was very much a physical transaction for a lot of counting stuff. I've got 5 goats, you know, and it's like, and, you know, other things might be counting, so you don't have to, you can think of this still as a positive number. A lot of accounting does that. You don't really deal with negative numbers. You just have kind of 2 sides of a ledger, and you're just kind of adding and shifting things back. But nowadays we like negative numbers. All right. Okay. Now, all right. Let's try some 2-digit subtraction. 27 minus 14. All right. What is it? How do we do it? So obviously we don't want to do the dots thing, right? That's absurd. So we can try it kind of the way that we did the addition, only by expanding it. 20 plus 7. Got 2 bundles of 10 and 7 units. And then I have 1 bundle of 10 that I want to take away from. And then for single things that I want to take away from. It's important to keep that minus sign, right? I'm taking away a total of 14 stuff. I can write it as taking away 10 and then taking away 4. All right, 20 minus 10? 10. It's the 2 minus the 1, comes the 1. And 7 minus 4? 3. And so that's our 13. Now, as usual, there's the bad way, which is 27 minus 14, and you start on the right. 7 minus 4 is 3, 2 minus 1 is 13. Again, it's bad because you start with the wrong digit here of what you care about. You care less about the 3 than you care about the 10. But again, we do that because of carrying reasons. And the good way, in this case, on the board, you wouldn't notice a difference. It's only through time and motion. 2 minus 1 is 1. 7 minus 4 is 3. Right? Okay. So when you don't have to kind of grab a 10 from the other side, starting from the left is just as easy or hard as starting from the right, but you want to start from the left because you get the right size. And you can also do, again, the rounding thing, right? You can do 30 minus 10, that's about 20. Here it's not a great estimate, but when you have a lot more digits going on, rounding is a quick way of getting something sensible. All right, so we need some other number to show the difficulties. So you roll some dice for me.
One, 9, 7, 7.
Okay, say 91 and 77. All right, so again, quickly in my head, I do 90 minus 80 is about 10, so I'm expecting something like 10. Now, when I do this, I do from the left, 9 minus 7 is 2. And now, here's for some serious magic. I have 1 minus 7, right? Now, we can't just do the like minus 6 thing. That ain't going to work. So the trick here is you look at this 7, and you say, okay, what do I need to add to 7 to make it 10? 3. So kind of like view this as sort of a 3 here, and now we add it to the 1. We write down 4, and we slash the 2 to tell us to drop it down by 1, and it's 14 is the answer.
Otherwise better.
Um,
No, doing the opposite direction.
Well, the opposite way is 91 minus 77. A lot of people mess this up too. So that would, I say 1, 7, and go, okay.
110.
What? I would cross the 9 out, make it into an 8, and then kind of have this be 11. 11 minus 7 is 4. And then 8 minus 7 is 1. So this gets pretty messy pretty quickly. And again, where are you likely to make a mistake? It's farther to the left where it's worse to make a mistake. Here, it's a simple kind of trick that kind of, you also have to do 11 minus 7, which is a little bit more harder than 3 plus 1. So let me try another one to get the technique. I don't know. 52 minus 31. No, 39. Let's go with 39. 31 would not be useful. All right. So again, in my head, I look at it and I say 50 minus 40, 10. So I already kind of know I want to round it 10. Now, 5 minus 3 is 2. Now I've got 2 minus 9. What do I need to add to 9 to get to 10? 1. And so 1 plus 2 is 3. Slash that, it's 13. So that's sort of how it works. Now,
James, I think you got some nerve introducing addition into a subtraction problem. It's also not represented anywhere on the notation. So I think that's where I'm getting tripped.
Do 1 plus 2.
well, it's about just keeping it in your mind. You look at 9, and you just replace it as the 1, and 1 plus 2 is 3, and you slash it. So you like Just convert and slash. I mean, if you like. You know, you could do 2 and then just like write a +1 here, and 3 and slash. That helps your notation as to what's going on. But it gets messier with bigger subtraction problems.
Is the slashing and underlining pretty consistent in your note taking in terms of like reducing or adding an integer, I guess?
Yeah, well,
The underline was not consistent. You had to abandon that.
well, I abandoned it because I did multiple numbers being added together. So you get above the 1. If you just stick with adding 2 numbers together at a time, you can just stick with the underline, and then it's completely the same as the slash and the underline. Declan?
Can you give us an example using this way of subtraction with larger numbers?
Want to give me some numbers?
153 minus 78.
Okay. So, 1 minus 0, it's just going to be 1. 5 minus 7, okay, now we got to do this flipperoo. So the 7 becomes a 3 in the mind. 3 plus 5 is 8, and we're going to need to slash that. And then the 3 and the 8, and 8 becomes a 2. 2 plus 3 is 5, slash the 8. And so the 1 becomes a 0, the 8 becomes a 7. 75.
All right.
Did that work? I check it by adding. Right? 78 plus 75. We got the 14, and then we have 8 and 5, which is a 3, and an extra 1, 153. That's what we started with. Oops. I should not underline that. All right. All right. Let's try 2, 3, 8, and then all right. So let's try this one out. So this is 15,328 minus 5,329. In my head, I think of this as 15,000 minus 5,000, so about 10,000. That's really the most important thing you need to do when you first see a problem. You know, if I'm buying a car for $15,000 and $328 and I get a 5,329 discount, what do I care about? I care about the 5,000, right? It's now about 10,000. The biggest thing you care about. Anyway, so drop the 1, 5 minus 5, that's 0. 3 minus 3, that's 0. 2 minus 2, that's 0. 8 minus the 9, the 9 becomes a 1. You add it, 9, and you slash it. But now it's a 0. So that didn't actually carry over anything. You slash this, slash this, slash this, that becomes a 0. And 0 slashed becomes 9. So 9,999.
That's the rules, Parker.
That's 9, ruined it.
Now let's try it the standard way, if you will. All right, standard way says 8 minus 9, oh, that's a problem. I want to make this into 18, make this into 1. 18 minus 9 is 9. 1 minus 2, oh, that's a problem. I make the 3 a 2, that becomes 11. 11 minus 2 becomes a 9. 2 minus 3, oh, well, that's a problem. Let's make that into a 12, and this is a 4. 12 minus 3 is 9. 4 minus 5, well, that's a problem. Cross that out. 14 minus 5 is a 9. So, leave it up to you which one is nicer in this example, but I personally would prefer actually doing this one, even ignoring the fact that I prefer to get the larger digit. Because notice when I first did this, you know, the 1 drops down, 0, okay, I already know it's kind of 10,000. I'm computing an estimate as I go along. And I'm only 1 off from 10,000. Alrighty, up to 150. Very nice. So, questions about that? That's subtraction for you. Let me try another one. 327 minus 562. Okay. Going left to right. 3 minus 5, a minus 2.
Can't do that.
Like, that's weird.
You gotta borrow from someone.
You got to borrow from someone, right? So, the other nice thing about going left to right is that you'd immediately realize something is kind of off here. Basically, this setup does not work. When the lower number is bigger. It's important to kind of keep that in mind because it's easy to forget. You're just like, I've got 2 numbers, I'm subtracting them. So how do I deal with this number? Well, 327 minus 562. 500 is bigger than the 300. And so I know I'm going to have a negative number. Will be negative. And so I put that in my head, and then I flip it. So 562 minus 327. And now I do my whatever I want to do. 5 minus 3 is 2. 6 minus 2 is 4. 2 minus 7, well, replace the 7 with a 3. 3 plus 2, 5, slash it, 235. And remember the negative, minus 235. Okay. Did I make a mistake? I could make a mistake.
Well, did you swap the 2 and the... Oh, wait, no, you didn't, sorry.
Okay. So, when faced with a larger negative number, realize you're going to end up with a negative number. If you're not doing negative numbers, you're just doing zeros. It's real easy. Just putting it out there for the zero theory. Like in Monopoly, you wouldn't compute out minus 235. You just say, you're out. Right? Remember the context. Okay. So, any questions about subtraction? It just goes on and on like that. Just add more digits. Let's see. I wonder if I don't know. Thought I had some. let's do some dollars and cents because it's eminently practical. $3.45 minus $1.89. Well, this decimal point will just go along for the ride. We pretty much ignored, except it just drops down. 3 minus 1 is 2, period. 4 minus 8, the 8 becomes a 2, because 8 plus 2 is 10. 2 plus 4 is 6. I'm going to slash that 2. 5 minus 9, 9 becomes a 1. 1 plus 5 is 6, slash the 6. $2.56.
You slashed the two.
$1.56.
See, this method lets you get the big numbers right relax.
You do lectures. And then the standard method would be 5 minus 9, put the 15 there, subtract this. 15 minus 9 is 6. 3, 13, 2, 13 minus 8, 5, 2 minus 1, 1. All right. So, there you go. Dollars and cents. Decimal points just drop down as you wish. We'll get more into decimal points once we have division under our belts, because that's what it actually means. But in terms of dollars and cents, most of us have a good sense of that already. Alrighty. What else do we need to know? So, for those who are wanting to learn some lingo, there's a couple properties of addition. There's we call the commutative property. And that's basically saying that 3 plus 4 equals 4 plus 3. Right? That's what this is. That when adding two numbers, you can switch their place. We don't really even think about it, right? I got 3 things, 4 things. Doesn't matter whether you count the 4 things first and then the 3 things, or the 3 things and then the 4 things, right? Seems pretty obvious. However, you know, again, it really does depend on context. It seems like it's sensible, but imagine that this sum is representing like an investment account. And the first term is what you add in 1 month, and the second term is what you add in the next month. Because of how investments work, giving you more money based on having more stuff, you know, putting the 4 first would actually end up with more money in the end. So even something like trivial, like switching the order, which, you know, we don't even think about it, depending on the context, it actually could. Again, like math is this thing that's trying to simplify our reality, dealing with stuff. Those simplifications don't always apply, and then the math stuff wouldn't necessarily apply. And then the other property at this point is the associative property. And that's basically grouping. So 3 plus 4 plus 7. I've written it without any kind of grouping, but, and then what would that mean? That would mean I've got 3 things, 4 things, 7 things. I take them all up, I throw them in a bin, and then I count them all out, right? That's what that would literally mean. We can also group these things. So 3 plus 4, you take 3 things and 4 things, throw them in a bin, count them up, and then throw in the 7 things, and then count. And of course you could do the 4 and the 7 together in the bin, and then the 3. So all of it comes out to 14. This becomes kind of a 7 here, and that's 14. And this is 11, and that's 14. Basically, associative says it doesn't matter how you group them. So that's the fancy term for that. There you go. That was probably like 4 years of math. I do want to just go over a bit of multiplication and division, the simple picture, so that we can start talking about it next time. So, everybody loves 2 times 3. Now, what this means is basically 3 plus 3. So I'm going to add 3 to itself twice. That's kind of the fundamental definition of what this symbol means. It's useful. 3 times 2 would mean add 2 to itself 3 times. Happens to be 6. Same thing. So basically multiplication is commutative is what these two things say. But notice it's a little less obvious than the addition. Addition was just count everything together. This I'm defining as add 3 to itself twice, and this one add 2 to itself 3 times. Wouldn't necessarily have to mean that it was the same thing, but it does. Pictorially, one great kind of technique is counting boxes. So I've got sort of 3 rows and 2 columns, and I count them up. 1, 2, 3, 4, 5, 6. So 2 times 3 is 6. All right. This box thing actually is pretty helpful for other stuff. And that's single-digit multiplication. All righty. Now, six divided by 3. So, what would that be? 2. So, what this means is we want to have 6 things and divide into groups of 3. It's one possible notion of it. So, 1, 2, 3, 1, 2, 3, and I've got 6. So I'm good. How many rows? 2. Or 2 groups. 2 groups.
That looks like a weird 3. 3 2 group.
3 2
Happy?
Yeah.
All right. Now, another way of kind of picturing it is I want 6 boxes. And I'm going to have, 3 rows. And then, I just draw in a line and I count up 1, 2, 3, 4, 5, 6. I'm good. So the number of kind of columns created that way would be the answer. I'm dividing this box up into thirds. Kind of 3 ways. I want 6 total boxes in the end. And kind of how many columns do I have? All right. All right. And then 7 divided by 3. How do I do that?
We get the remainder.
So I've got 7 things. And I want to divide it into 3s. I get 1, 2. So it's 2 with 1 left over. So that's the remainder. Now, there's also another way of kind of thinking about this. Let's say I've got things I can break up into better chunks. Let's see. It's flipping the thought process here. Into groups of 3. Yeah, this is a slightly different question is how many groups? Well, no. This will work. So 1 group of 3, 1 group of 3. And then this isn't a full complete group of 3, but it's sort of a 1/3 of a group. So instead of saying kind of remainder 1, you kind of think more in terms of the group and how much of it is filled. And so then that's sort of the fraction where it comes from. 1/3 of a group. Like that. Okay. I think that's probably more than enough. Any questions? So next time, multiplication and perhaps some division. Like actual computing out division stuff rather than the single digit stuff. And no doubt doing things in the wrong way from standard stuff. All right.